Today, we are thrilled to be joined by Mike Mahoney. Mike is a PhD candidate at the State University of New York College of Environmental Sciences and Forestry, trained as an ecologist/environmental scientist. Mike specializes in developing tools to make complex, broad-scale systems more accessible to humans, combining, for example, predictive modeling and visualization. Mike's professional activities have included data analyst, software engineer, and perhaps most importantly, chicken farmer. In today's webinar, Making Sausage, how and why open source scientific software gets made and what keeps us from making more, Mike will discuss how open science depends on open source software, tooling that lets, number one, users and researchers see what algorithms they're actually using to analyze their data. Secondly, lets members of the community weigh in on best practices and bug fixes. And thirdly, lets anyone involved in a project utilize tools no matter their budget or institutional affiliation. In fact, much of the open source science used by scientists is also primarily developed by scientists. Mike will highlight some of the motivations that drive developers to release open source scientific software, as well as what makes maintaining those tools rewarding. Mike will then discuss the institutional and cultural barriers that make it challenging and potentially threaten the long-term sustainability of these projects. And with that, I will hand it over to you, Mike.
Thank you. And thanks everyone for being here. Let me go ahead and get my slides up. Someone yell if that's not sharing, but...
That's perfect. Thank you.
Awesome. Yeah, so thank you so much, everyone, for being here. Thank you so much for having me. I'm really excited to talk with you all about the mechanics of how the sausage gets made, why people spend the time developing open source tools that enable scientific discovery, and these sorts of barriers that make it harder, and then hopefully a few ideas about what we might do to address those barriers, both at an institutional and an individual level. That was an absolutely fantastic introduction, but just to add a little more about my personal background. So I am a PhD researcher in environmental science, hopefully defending in just a few months if everything goes to plan. But in that line of work, I'm really focused on applied research activities. So I'm part of this group, CAFRE, the Climate and Applied Forest Research Institute, which is using open source technology to try and build models of how much carbon is stored in forests across New York State and how that's changed in the last 30 years in order to inform New York State's net zero carbon goals. And so I really do live in the world of users of open source scientific tooling. I spend the majority of my time actually doing scientific inquiry, trying to build models to understand the world around us. But in addition to that, I also am a developer of these tools. So for probably about 5 years now, I've maintained a number of packages for the R programming language that implement a number of different utility functions. So my specific focus area tends to be either in visualization or in spatial modeling. And so the packages that I maintain are bits of code available for anyone else to use that contain functions to make it easier to build and assess spatial models or to visualize the outputs from them. All this code that I'm releasing is stuff that I'm personally using in my own research activity. So it's code that I was going to write anyway in order to get things done in my day-to-day work. But I've put in a little bit of extra elbow grease in order to turn it into something that other people can install and use in order to drive their own research activity. And so the first thing that I'm going to talk about today is why bother doing that? Why bother spending that extra bit of time to make these programs that I'm writing open source and accessible for others in the community to also use? Now, before I get too deep into that, I do think it's useful to start off defining what I mean when I'm talking about open source software. And specifically, I'm going to be using this definition, which is adapted from the Open Source Institute's framework for what makes a project open source. They've got an 11-point checklist. I've got a sentence. So there's some nuances that are missing here, but I think it accomplishes much of the same goal. For instance, the definition here that all users of the program have access to the source code of the program and are allowed to redistribute, modify, and use the program as they see fit. That really gets to the core of what I mean when I'm talking about open source programs. I'm talking about programs that you as a user have the right to investigate to see what's actually running when you run a piece of code, and that you are allowed to modify to serve your purposes better, and that you are allowed to give either the original or your modified copy to whoever you'd like. Now, importantly, this definition does not mention anything about money. And I think that's a key misconception that comes up a lot in this space. There's no requirement here that open source software be free. Now, because anyone can redistribute your program, it generally is free because you've got a lot of competition if you try and sell it, but it's not a requirement. Conversely, it's not enough to just give away a piece of software for free. If you have a binary that anyone can download and execute, it's freeware, but it's not necessarily open source unless someone can actually see what your code is doing, if they can actually see the source code. The other side of this is that there's nothing about money when it comes to the developers either. So I think there's a common misconception too that all open source code is written by people who are effectively volunteering, which can be the case. There are people who spend nights and weekends working on open source programs that they're releasing. But much more commonly, in my experience, people are doing it under the auspices of some other position that they hold. I personally have never written open source code for free. I've done it either in my role as a PhD candidate or professionally as a software engineer for companies like Posit, previously RStudio, developing open source software full time. So the focus here is really on the freedoms that you as a user have when it comes to open source software. This idea that you are allowed to access the source code and use it as you see fit. Now, sorry, I clicked off my slides. Now that gets to one of the big reasons that I personally find it valuable to spend the time cleaning up the code that I'm writing for myself so that I can release it as open source, which is that doing so makes it a lot easier for myself and for others in my domain and in my field to practice open science practices. I'm sure that this is becoming an overly familiar graphic for at least some folks now that we're in October of the Year of Open Science. But this is the list of objectives from NASA's Open Source Science Initiative. And I think that all of these objectives either require or strongly encourage using open source tools to actually do your scientific analyses. When we're talking about what it means for an analysis to be transparent, for instance, I don't know that you can say that you can understand or have your results be visible if you're not able to see the actual code that's running the algorithms that got you to a given result. Now, there's no requirement that you actually spend the time looking at it. You are allowed to trust the tools that you're using. But if you don't even have that ability, it makes the amount of visibility into an analysis that you have available to you, it reduces that in a really substantial manner. Another consideration here is that when we talk about reproducibility is extremely helped by using open source tools. So if you, for instance, are uploading your code and your data to Zenodo or to Dryad or wherever else, whatever repository after an analysis is run, because you have the freedom to redistribute your open source packages, you could also upload those packages as they exist as you're using them alongside your data and code so that people can reproduce your entire environment. This is not exactly common. It's becoming a bit more common as a lot of tools are coming online to containerize an analysis and let you upload that container as a unit. More common is that because open source projects generally are released alongside their version control system, that version control basically is a system that tracks the changes that are made to a code base over time. That allows you to unwind those changes and go back in time to the state of software as it existed when a given analysis was run. And that means that you have the ability to access those previous versions of that open source software in order to replicate a computational environment. That's a huge win for reproducibility. And that's something that really doesn't exist with proprietary software, where you're limited to whatever versions of the software a vendor makes available for you. I think this is becoming even more important as we move to an increasingly cloud and hosted services environment where vendors have the ability to update software more or less as you're using it without you necessarily noticing that things are being updated. I think that's a real threat to reproducibility in the long term and is something that we aren't really giving enough thought to as we're using these closed source services. And then last but not least, as far as accessibility and inclusivity goes, there's some obvious wins from using open source when it comes to including people who don't have institutional ties, who don't have huge amounts of resources to buy licensing fees and similar costs. But even beyond that, using open source technology can make it a lot easier to include people who just don't work in the same domain as you. Because a lot of the times when we're talking about proprietary software systems, the software that is being used for analyses in economics doesn't line up with that's being used in psychology. That doesn't line up with what's being used in ecology. And as a side effect, the technology that we're using, if we're using proprietary software that not everyone has access to, can help lock us into our domain silos. And open source represents a positive way that we might be able to get beyond those. So part of the reason that I spend the time developing these tools in the open and releasing them for others to use is that I do care about following open science practices as much as I'm able. And this makes it easier for me to follow best practices here and for others in my field to do so as well. There's also some more selfish benefits that I get. Open source makes it a lot easier for me to collaborate with other people. When I'm releasing an open source project, I'm effectively just uploading a set of files and folders that are on my computer to somewhere on the internet, which makes it that anyone who is interested in my software, who has access to this URL, is able to give me feedback on this project. They're able to see my code, they're able to find bugs, they're able to give me suggestions for improvements. Now, I'm not going to pretend that most people who are just on the internet are going to care about my project or have useful comments about it. But because this is available to anyone who is interested, you wind up being able to attract your more technically experienced users who might have some curiosity about how the software that they're using actually works under the hood. And as a side effect of that, those users are going to be the ones who are most familiar with how your software works in the real world and the most capable of finding things that don't work as they expect or don't work as well as they would expect. There's a quote from about 40 years ago now that given enough eyeballs, all bugs are shallow. And releasing projects in the open makes it a lot easier to get more eyes on your project than if all these files simply lived on my computer or if I was having to email a zipped folder around. Now, the really cool thing here is that these collaborations don't necessarily need to be synchronous either in a way that they generally do with more closed source projects. So for instance, I last year wound up opening this issue on this repository CAST, which is a relatively specialized piece of software. It's utilities for spatiotemporal modeling. And I opened an issue saying that there was a bit of a difference between how a statistic got calculated by the software versus in the paper that described the software. The maintainer of this package, Hannah Meyer, and I discussed this for a minute, and then we wound up making a change to how the package works. So now I, as a user, benefit from this improved version of this package. The other users benefit from the improved version of the package. Great. 6 months later, someone else comes along and says, hey, this change that you and Mike made actually has a different bug in it. We wound up introducing a new mistake with how we wound up addressing things. And so the new issue is opened. This researcher and Hannah go back and forth about this new bug that they've identified, and they wind up fixing it. They commit the changes. Myself, this person, every other user winds up benefiting from their contributions. I have no idea who this person is, and I'm still able to collaborate about this specific piece of software with them over space and time without ever needing to actually interact with them directly, enabled by the fact that anyone who is interested can see the changes that I made 6 months before this issue was opened. And that's really exciting to me. Similarly exciting, first off, there's becoming more and more attempts to sort of standardize this type of collaboration. For instance, through our open science software peer review system, which treats software in the same way that we would treat a journal article or other forms of publication. If you are writing an R package, you're able to submit it to our OpenSci, and they'll assign your package an editor who will go and find reviewers who will work with you and with each other to identify areas of your package that could be improved and perhaps even how it could be best improved. So suggestions for code to incorporate. And I think that this is really exciting. It's a type of collaboration around the tools and how we actually calculate and how we actually run analyses that we haven't seen a ton of in the past. Now, another really cool side of doing things in the open in this way is that these contributions and these improvements can be cumulative in a way that isn't really possible with a lot of other modalities of working. So for instance, if you look at the network of all packages on CRAN, so that's where you download our packages from. It's R's version of like PyPy or NPM, if you're familiar with those. On this graph, these blue dots are individual packages. The black lines are linkages between them. And when I say linkages, I mean that these are packages that are actually using pieces of code contributed in the other packages. They have dependencies on other packages in the ecosystem. And what you can see is that this is a really densely linked network. These packages rely on each other really deeply, which means that as you make changes to one part of this network, those changes can wind up percolating much further away than the original package. For instance, a different way of looking at this same graph here, the dots are red if they depend on this one package isoband and gray if they don't, but otherwise it's the same set of packages. It's now white lines instead of black for linkages. Those red packages are about a quarter of all packages that were available on CRAN when this graph is made that depend on this one package isoband. Now, isoband is a really specialized piece of software. What it does is that if you've got data in some abstract 2D space, isoband calculates contour lines around that data so that you can wind up graphing it in a way that looks like a topographic map, but for densities of data rather than elevation, called a contour plot. And it winds up having these 4,000 downstream dependencies. Not because 4,000 separate packages decided that they needed the ability to draw contour lines in abstract space, but because a handful of visualization libraries wind up relying on isoband to make that type of visualization. These other packages then rely on those visualization libraries and gain all of the capabilities that are exposed by that piece of software. That means that all of these packages, whether or not they've ever thought about what a contour plot is, have the ability to generate contour plots. They pick that up automatically from this upstream dependency. And when an improvement is made in isoband, it winds up improving all of these downstream nodes in this network, which is really exciting. There's a quote by a mathematician, Anne Whitehead, that civilization advances by extending the number of important operations we can perform without thinking about them. And I think that this is sort of one of the purest examples of the concept. This idea that improvements in how we calculate the most specific of these statistics can percolate throughout this network without anyone needing to notice that it's happening is really exciting to me as someone who's working in this space. And then last but not least, I generally find that releasing things as open source technologies aligns well with my personal goals as a researcher, as well as what I view as being the goals of the scientific enterprise more generally. What I mean by that is that, well, about 10 years ago, Jeff Leake wrote this blog post that if there is no code, there is no paper, making the argument that especially if you're working in methods-oriented fields, so here, stats and computer science, if you aren't releasing the code that either backs up your assertion that actually runs your analysis, or if you're introducing a new method, if you aren't releasing the code that implements that method, you are abandoning one line of evidence for whatever argument it is that you're making. By not making that available for other people to either see themselves or use for their own purposes, you're making people either have to simply trust your results as they are presented or translate from your paper into their own code and do a huge amount of work to actually assess your claims. Releasing the code means that you don't have to do either of those. It makes it a lot easier for people to actually trust the results that you're putting out. And I think that this is why more and more we're seeing more calls for including code alongside data when people are archiving projects. Now, the other side of this is that if you are releasing your actual code that implements a method, which is a lot of the software that I work on, it makes it a lot easier for people to actually use that method if they don't need to program it themselves. And so selfishly, from a careerist perspective, it is good for me if people are using the methods that I'm introducing. And so I should want to make it as easy as possible for them to do so. Now, the one concern that I do hear when I talk about this part of things is this idea that releasing your methods in this form makes it a lot easier for people to critique them or for people to fiddle with them and maybe find variations and perhaps scoop you on getting to alternate versions of your method before you could. Personally, this is a concern that I understand but don't share. To quote a different mathematician, I'm not worried about being scooped. I'm worried about being ignored when it comes to getting my methods used in my field. And so personally, it makes sense to me that I want to, as much as possible, get more people using the methods that I believe are the best way to address scientific research questions. And anything that I can do to make that easier aligns with my personal interests. Now, all that said, these are the reasons that I personally am engaged really deeply in working with open source technologies, why I write code and then release it for other researchers to use. And it's the reasons that a lot of other people get involved in doing this type of work as well. But I want to talk now, shift our focus a little bit to why people stop doing this type of work, the sorts of things that threaten the sustainability of open source scientific software, both on the individual project level and at a slightly larger systemic level at the same time. The first one being that, generally speaking, open source is a really lonely field to work in. This can sound really counterintuitive because I've been talking about how open source enables a lot of collaborations with a lot of people who you wouldn't interact with otherwise. But if you look at who actually contributes to any given project, you generally see the same pattern repeated over and over again. So for instance, looking at CAST, which I had the screenshots of a minute ago, looking at the number of authors who are committing to CAST, a commit here is effectively a change to a code base. It's a funky metric. Not all changes are the same size, but it's pretty much the best way of measuring who's actually contributing to a project. And what we can generally see is that on CAST, we have a single author, Hannah Meyer, who maintains the package. Hannah's actually also in the second position here, just on a different account. And that means that all of the work of actually maintaining this package and writing this software falls to Hannah. That has some important implications. It means that if you are trying to figure out how to do something that's particularly challenging, something that you might not be familiar with, that is hard, you don't really have a community that you can draw from. There's not anyone else who understands your software or understands the problem that you're trying to solve at the depth that you do, which means that you're pretty much out in the cold when it comes to actually solving these hard problems. The other side of it is that there's a lot of sort of drudge work that goes along with actually maintaining an open source project. There's things that just break around you all the time. So if you're linking to other websites and those links die, or if some package that you're using winds up updating its interface and you need to update yours to match, there's a lot of sort of chores that fall entirely to you as the main developer because there's not anyone else who's involved with the project to really help. And this, of course, is a relatively small piece of research software. This is written by an academic who is working more or less independently on it. But you see this pattern just about anywhere that you look. So for instance, if we look at dplyr, which is one of the most popular R packages instead, the main difference is that the number of people who have contributed once to this package gets a lot longer, but otherwise our graph is about the same shape. If we zoom in to just look at the top 50 committers, what we can generally see is that most of the work is shared by here 2 people who actually worked on this package. Really, there's a team of 5 people who might have some degree of familiarity, but it's still a relatively small team working on this piece of software relative to the number of users. And this is a package that has a for-profit company backing it. There are people who are employed to work on this piece of software. If we move outside of the R ecosystem, if we look at Python and Pandas, which is perhaps the most popular piece of data science software that's available right now, we see more or less the same shape graph. And when we zoom in, we can see that there are a lot more people who have contributed to this package a handful of times, but the vast majority of development effort still gets concentrated among a small handful of people. Now, particularly for these larger projects, that has one other implication, which is that as your community of users grows, you start getting a lot more requests for support from your community. That can be in the form of educational materials, so introductions to how to use the software. That can be in the form of effectively asking for consulting work of how do I solve this specific problem. And then it also can be in the form of things like bug reports or feature requests. And importantly, most of those interactions are going to be negative. Now, I don't mean toxic. I don't mean that people are being purposefully mean. Most of the time, people in the open source space are not being purposefully mean. But when people are writing you, it's very rarely that they're writing you an email to tell you how much they love your software. Usually, they're writing you saying that they found a bug, or that your software didn't do something that they were expecting it to do, or that your educational materials that do exist aren't good enough for them. You're getting negative feedback. You're getting things that need to be better pretty much exclusively from your community. And so as your community grows, you get more and more of that negative feedback, and it's still really falling on a small number of people. And that can be a huge contributor to burnout and to a lot of these projects slowly dying off or going dark, especially as you start hitting more moderate levels of success. I really like, there was a quote that I saw on Mastodon the other day. Running a successful open source project is just goodwill hunting in reverse, where you start out as a respected genius and end up being a janitor who gets into fights. And it's really true. There's a lot of projects that intentionally step away entirely and stop releasing the project as soon as it hits a certain threshold number of users because they aren't interested in life as a janitor. Now, a separate contributor to burnout is that open source, generally speaking, is a long-tailed phenomenon. And what I mean by that is that the majority of open source projects exist in this long tail of usability. So if we look at all our packages available on CRAN, I haven't done the proper amount of cleaning, so people might notice that the number here isn't quite right, but this is the number of times that all our packages were downloaded in September. The heights of each bar is the number of times it was downloaded. And what you can tell is that there's a handful of bars here that are visible, and then the vast majority of these packages are effectively not downloaded. They are a rounding error number of packages. In fact, it's about 1,000, a little more, that make up 95% of all package downloads. Now, that means that there are 25,000 packages that are pretty much downloaded never, that make up only 5% of downloads. But I have 3 separate packages that are in that 5% that together have been cited more than 30 times by people who are using them to implement methods, that are using them to drive their science forward. And that means that a lot of work is being spent on things that are used relatively rarely, but are still powering science that people care about. Now, if we zoom in even further to just look at 90% downloads, it's about 600 packages that wind up making up 90% of all package downloads. And as you can see, it's still very few packages that are massively successful on the left there. The majority are still in this tail where they're downloaded a handful of times, but not a ton. I've got a package here. It's the red bar in the very middle. If you can't see it, that's kind of my point. It's this package called RSample, which powers cross-validation that a lot of people use to assess their models. It's been cited about 30 times this year by people who are using it to make sure that they're assessing their models in a scientifically, statistically sound way. And that package, is very important for those users, but it isn't one of these bombshell packages. It's not downloaded tons and tons and tons of time. And that means that it's outside of the scope for a lot of these support structures that do exist for people developing open source scientific software. There exist grant programs, there exist institutional support for these projects, but they generally are focused on the left-hand side of this graph. Those projects need support. I'm not trying to criticize that, but it does mean that the vast majority of people who are building open source software that's being used in science, those people aren't receiving that type of support, which can threaten the sustainability of those projects down the line. Particularly because open source developers mostly are not professional open source developers. The vast majority of scientific software that's being used in science is developed by generally its academics because they don't feel the need to ask before they upload something to the internet. Increasingly, there are more and more people in government, in industry positions who are also developing open source scientific software, but the vast majority of them work for institutes where their position is something else. They are staff researchers. They are in other positions than specifically an open source developer. And so it can be very difficult to make work that's being done to build these tools legible to those institutions in a way that counts as far as career evaluations go. And that can really threaten how successful these projects are in the long run, because it can be really difficult to justify why you're spending the institution's time and money on these activities when it's not something that's necessarily within the purview of what we think of a staff researcher's job being. Contributing to that, open source success is really difficult to track. It can be really hard to actually tell how successful any given project is. The metrics that we do have available tend to be things like downloads or maybe citations, which is what I've been using, but those aren't really useful. They can be really misleading, especially with things like downloads. If you release a new version of your package every single day, you're going to get more downloads than someone who releases once a year, even if you have the same number of users. Talking about citations, if you have a core library that is really essential to how a lot of computations get done, and then you've got wrappers on top of that that make it a little more friendly for users, users often cite the wrapper that they're using and not the core library underneath. And so the thing that is arguably more important to the ecosystem doesn't collect that usage statistic. So it can be really difficult to translate the success of an open source project into terms that these institutions can actually understand. So all those challenges put together can make it really difficult for open source projects to stay sustainable in the long term, to actually survive and continue powering research for a number of years. This is my second pivot point in this talk, which is to start talking about what we might actually be able to do to address some of those. And first and foremost, I think the thing that has been most successful when it's been tried is that programs that provide small, lightweight seed funding to these projects can be extremely impactful. This is something that Annie Burgess, ESIP Labs director, has been talking about for years, and she's right. She's correct. This is something that can mean a lot to the success of these projects. The amount of money that you actually have to give a project to increase its sustainability massively is really small, because most of the developers aren't relying on your funding to actually fund their position. Most of these developers have positions as professors, as research staff. But what these programs do is they can legitimize the project in the eyes of their institution. They can make it so that these people can justify the time and effort that they're spending on these projects to the people who they have to justify their time to. My favorite example here is that back in 2016, these two professors from Europe wound up pitching the R Foundation on a $10,000 grant. And you can see down the bottom here, it's a little small, sorry about that. But you can see on the bottom here, this $10,000 employed a student assistant for 10 hours a week and a travel grant, and then a second travel grant. We're not talking about funding people's positions here. This is not a full-size research grant. But this $10,000 project winds up seeding this package that then these professors can say to their institutions, look, the R Foundation believes that this package is useful. And this winds up becoming the SF package, which now is pretty much core to how spatial analysis gets done in R. Since 2018, the package has been cited more than 2,000 times, and it's the 14th most popular R package, all seeded by a $10,000 grant. Now, importantly, the other side of this, that these grants be lightweight, is just as essential. You have to avoid the administrative overhead associated with these programs, actually outpacing the amount of money received from the programs. But if you're able to strike that balance, this can be an incredibly powerful way to help people who, again, are not trying to fund themselves based solely on this project. It can be a really useful way to legitimize these projects in the eyes of other institutions. Separately, another huge help for the sustainability of the ecosystem is the existence of community groups. In particular, my personal favorite of these groups is one that I mentioned earlier, rOpenSci, which, in addition to their peer review program, also have programs for providing spaces for developers to come and talk with each other, both to get that sort of community of experts so that if you do encounter something difficult with the maintenance process, you have this community that you can reach to for help, but also to provide a sense of community so that it's not as isolating to be working in open source development. The other side of most open source developers not doing that professionally full time is that most of the people who they interact with in their day job don't do the same thing as them and don't really understand what it is that they do. So these community spaces can be extremely helpful for reducing that sense of isolation. There's starting to be more and more communities that are trying to provide this service. For instance, PyOpenSci is a relatively recent community group that's trying to replicate our OpenSci's model, but for the Python scientific ecosystem. And I think that's fantastic. I think we need more of those. So these groups really need our support wherever we are able to give it. Now, 3 out of 4 here. I think also if you are a person who does any sort of career evaluation, think about ways to include software in that process of evaluation and value software as a research output in and of itself. Right now, our general model for making software development count for academic careers is to put it through things like our OpenSci's peer review system so that you can say that your software is peer reviewed, or publish short papers describing the software in venues like the Journal of Open Source Software so that you can say that you have this paper associated with the software. These are great ways to make software legible for academic evaluation approaches, but I think that they are kind of a crutch that are trying to shoehorn research software development into something that these academic institutions already understand and already have ways to evaluate. If we're able to value the development of research software as an activity that researchers should do in and of itself, I think that we would make it a lot easier for people to justify to wherever they are based why they spend time developing these tools that other scientists, other researchers wind up using. And then last but not least here, if you are an individual, if you don't have connections to the purse strings or to tenure evaluations, I'd like to encourage you to cite your software that you're using. If you are ever publishing any sort of paper or report, it's extremely useful if you cite your software, both because it helps me make my software legible to the people who I am responsible to, but also is a very useful motivating factor. Even if it's not in a journal publication, but if it's on somewhere that has the .gov, the .edu URL, that can be extremely useful for me to turn around and say, look, other people are using these tools and it is useful in this community of scientists that I exist in. So as much as possible, if you cite the tools that you're using, it'll make it a lot easier for people to keep building them for you to use. And so with that, I want to say thank you. If you are interested, you can find me online. I'm at mm218.dev or Mike Mahoney 218 on just about everything. And then these slides are available off my website. Thanks.
Mike, that was awesome. Thank you so very much. I did see a comment in the chat that the URL did not work to get to your slides.
Oh no, I know that if you are on some government
we can
VPNs,
work
that can wind up not liking the .dev URL, but I'll put the link to, I saw someone else did too. I put the full link.
Yeah, no worries. We can get that and we'll get it out to everyone if that's okay with you. I have to say to start off that I loved your title, making sausages, because I really don't know what goes in. I don't want to know what goes into making sausages, but we need to know the good, the bad, and the ugly. And you kind of just presented that, like what's good about doing open source software, what the challenges are, and then what we can do to mitigate that. So I just wanted to say that first and foremost. Love that. We will take any questions that anyone has. And so, if you'll just raise your hand, I can call on you to ask Mike a question. But I also will tell you, Mike, you're getting so many kudos in the chat. People loving your Goodwill Hunting and all of that. Fantastic presentation. Can't wait to share this with colleagues. So someone did ask if this is going to be on YouTube. We are recording this, and we will be providing a link to the recording on our ESUP Open Science wiki page. And so as soon as we get that done, we'll send that out to everyone. So while we're kind of waiting, I'll start with some questions if that's okay. So you mentioned being scooped, and I used to be the community coordinator for TOPS and transformed to Open Science, and that was the prime question we got, right? Like, I don't want to be scooped. That's my fear. And you mentioned your biggest fear was being ignored, right? Do you have other words that you could tell people that are worried about that scooping happening to them?
Yeah, so I had cut a quote from the talk at risk of it being more quotes than anything else. But there's an Andrew Gelman post from a number of years ago where he talks about the point of science is not to build beautiful careers, it's to understand more about the world around us. And personally, I try and center that as much as possible when I'm doing my work, is that the reason that I'm doing these things is not to establish a beautiful career for myself, but because I am interested in understanding more about the world. And particularly with my research area, I'm interested in making it easier for others to understand the places and things that they care about. So where I'm sitting, that's what's important to me. And making it easier might include releasing my version of an idea so that someone who sees it differently can improve upon it. And I think I have been lucky enough to be in a field where I have never had a desire to like, oh, I wish I had more ideas for what I should be working on. I have always had far, far, far more ideas than I will have time to address. So I think that you start off, first off, with such an advantage, such a head start, if it is an area that you are working in, compared to anyone else who's going to come along and look at your code just by the familiarity that you have with it. And as a result, if you have a follow-up question associated, you are the person who is best positioned to answer those questions. And if it's something that you wind up pivoting away from, having it out in the open means that those questions might actually get addressed in the long run. It makes it a lot more probable, at least. So if it's something that you are interested in the answer to, working in the open in this way makes it a lot more likely that anyone else can actually take up that mantle and lead the charge there.
That's great. Thank you so much for those words. Any questions from our community here? Well, I have another one too. You mentioned what we can do, and another thing so this is part of our incentives kind of area of focus. And you mentioned, valuing software as a research product. Have you had to advocate for that at your institution? And if so, do you have words of wisdom for those out there who are in academia who, need to advocate to get these things included in TNP and stuff like tenure and promotion and things like that?
I've been very lucky that my chain of command specifically is very recognizes the value of these as research activities. I will say that for when I go more broadly, I have had people, I've described what I do for my dissertation, and they go, okay, but what's the science? Because a lot of it is, well, how do you visualize these ideas in the first place? It's not something that I really have found a great answer to. So I'm actually currently, if you can tell by the hotel art behind me, in Chicago for the first ever meeting of US research software engineers, which is an attempt to establish effectively developing research tools, methodologies as a career track in and of itself, adjacent to rather than overlapping with traditional academic careers. And I think that the best answer that I have heard this week for how do you measure, track, and recognize effort here, the best answer that I've heard has also been, we don't really know yet. This is all still very new.
Yeah, that's a great answer. And, I think please provide us insight as you attend this conference and find out more. We do have a question now from Rob. And Rob, if you want to come off mute and ask your question, that would be great. I will say, Mike, you have to read the chat when you get a chance, because I cannot even cover all the words being said there. And there's some great chatter there. And again, great kudos to you there. So make sure you read that. But Rob, feel free to ask your question.
Yeah, thank you. This is a great presentation. At my company, we find ourselves dealing with open source all the time, and we frequently make use of code that are made by external developers communities, in fact. And I was wondering, what is kind of the most proper way to be able to work with those external supporters of software who may either be very slow and deliberative in the changes that they employ, that you may need to have something actually changed quickly, or maybe have somehow abandoned their software. I think eventually somebody just simply can't sustain a code base anymore. What are the kind of patterns we can see for sustainment in the long term?
I think that especially in this situation, so if I'm understanding correctly, you're at a company that's using pieces of open source that exist out in the ecosystem, right? So what I've seen in this place is, particularly assuming that you have pieces of your stack that aren't open, I've seen companies that maintain an internal fork that they, as much as possible, are attempting to contribute to the upstream. So they're attempting to make changes to the original version of the software, but maintain their own internal version that's a few steps ahead. Now that is an amount of overhead, especially if the versions that the maintainer is merging aren't aligned with what you've done internally. Like, it's easy for that to get out of step, but it does mean that you can still benefit from all the benefits of the open source project while also getting critical improvements at the speed that you need them. The other side is that I think it's become, well, there was a golden era of companies forking or releasing their own versions of software, and this especially when you're talking about projects that seem to be effectively abandoned or at the very least aren't maintained with any vigor. There was an era, especially like 2017, 18, where Twitter, AWS, and a lot of other large companies were maintaining effectively forked versions of projects where they were saying, like, yeah, the direction that this original project, either it isn't progressing anymore or we have alternative needs. And especially if the project is more or less abandoned and you're able to maintain that as an open fork, that can be a huge way to return that value to the community as well. And so that's, I know, like Twitter especially, there was a ton with like caching and a lot of the DevOps side of things that used to be Twitter products in the before times.
Great, thanks. Thanks, Mike. We have another question from Sam.
Hi, thanks for your talk. It was really interesting. I work at UC Berkeley doing open science, and I've been in a bunch of conversations with different campuses that are developing open source program offices. And I'm curious what your opinion is on that. Do you feel like that kind of centralized resource is useful? It kind of parallels tech transfer offices and IP offices that often exist at universities, but in this case, as a way to kind of like bring all of the open source projects on campus together. Do you feel like that would be helpful, or is it like just more bureaucracy that doesn't actually dovetail with the true work of this kind of work?
I think that, as you were pretty much saying, it can go either way. It's new enough that I don't know that there's a ton of examples out in the world, but I've encountered open source program offices that are very beneficial at accelerating, especially if they're able to answer the common questions that people have when they're starting to develop open source projects, especially around things like licensing and legal risk, especially as the EU continues to move to shut down open source development as best as possible. So if you have especially the legal resources available for people who are interested, it can be a huge benefit there. I think the failure mode that's common is, as I sort of, glibly said in the talk, a lot of the times these open source projects were written by academics because they didn't feel the need to ask anyone before they put it out there. I think that that's sort of the failure mode, is when these open source program offices wind up becoming a little more like the tech transfer office, where they become this wall that's very concerned with protecting the IP and the patent rights. And if you approach it from that direction, I do think that that's going to introduce an amount of overhead that all of a sudden no one is willing to coordinate with that office. The other side of it is the degree of centralization that these provide. I was talking with someone yesterday who was talking about they ran or still run a data science center at the University of Arizona, and they just hit their 5-year anniversary, and they were going through a review process, and they were being asked, what is the future of the center for the next 5 years? And their answer was, we shouldn't exist. We should have devolved this capability to the departments that we're interacting with. These capabilities should live in the departments. And I think that especially if you're at an institution where people are developing tools that should be open sourced in multiple locations, a model where you are able to embed with those departments, that you are able to go to them rather than requiring it to be a centralized people coming through you in this pinch point. I think that that can be very useful for accelerating and for improving the quality of these programs.
Thanks.
Great. Any other questions for Mike? We probably have time for one more. I think you've covered so much, Mike, and I just want to say thank you again for joining us today. This has been so insightful, and as you see when you read the chat, people were saying this was such a fantastic talk and so useful to what they're doing in their everyday institutions, and you're getting claps right now and all that. So claps for you. So thank you so much. Just for everyone else, I'll mention that we are having the program manager next month for the Higher Education Leadership Initiative for Open Scholarship, and that's Helios. Come and talk to us in our webinar series. The other thing I'd like to mention to everyone, as we come up on the end of the year, which is weird to say, Jenny and I will be stepping down as co-chairs of the Open Science Cluster. We've so thoroughly enjoyed co-leading this cluster, and having this webinar series has been so insightful and powerful. And so as we step down, if you are interested in chairing this cluster, please contact us. Please email us, and we'll gladly share our thoughts and work with you to transition. Jenny, would you like to share anything? And again, Mike, I just want to say thank you. That was so incredible. Jenny, would you like to say any closing words?
Thanks, Cindy. I just simply wanted to concur. Thanks ever so much, Mike. That was a fantastic webinar, and obviously generated a lot of chat and a lot of questions, which is wonderful. And our last webinar will be at the usual date, the 4th Tuesday of the month. So it will be the 28th of November, same time, same place.
Thank you all. Claps for Mike. Great. Thank you so much.